Nowadays, more and more devices require access to the internet. To meet these ever-increasing demands, next-generation networks, also known as 5G, promise staggering speeds by 2020. To achieve this, 5G combines four key technologies: C-RAN, millimeter wave, network densification, and massive-MIMO. First up, technology number 1, Centralized-Radio Access Network architecture. C-RAN proposes the separation of the baseband unit from the remote radio heads and their placement in centralized locations, where it is easier to provide cost-efficient energy supply and climate control. Next up, technology number 2, millimeter wave. Millimeter wave, unlike current licensed spectrum, can offer a huge amount of bandwidth that enables unprecedented wireless speeds. However, this comes at the cost of high path loss, which leads us to technology number 3, network densification. The dense antenna deployment allows the operators to reuse the spectrum. In parallel, the antennas are placed closer to the user, which facilitates the introduction of millimeter wave radio. Finally, technology number 4, massive multiple input, multiple output, refers to the massive deployment of antennas. Massive-MIMO provides higher spectral efficiency by spatial multiplexing of many terminals in the same time-frequency resource and high energy efficiency, as the array gain permits a reduction of radiated power. In parallel, antennas get shrunk as frequency increases, which permits the placement of many millimeter wave antennas into a limited space. The combination of the aforementioned technologies, however, into a single viable network isn't a simple task. For instance, the combination of C-RAN and millimeter wave requires many miles of newly deployed fiber, which involves significant cost. In parallel, the overhead of the digital common public radio interface, the protocol used for the BBU RRH communication, becomes prohibitive as the number of antennas and the used bandwidth increases. And this is where 5G PHOS steps in. 5G PHOS heavily invests in cutting-edge integrated optical solutions to support the aforementioned technologies. Specifically, 5G PHOS exploits laser arrays, where the wireless radio frequency signal gets modulated by a continuous wave carrier optical signal and converted into optical. Optical Beamforming Networks. When an RF signal hits an antenna array, each antenna element receives the signal at a different time. Therefore, OBFNs add proper delays to the signal received by each element, so that a synchronized signal is transmitted to the rest of the network. Finally, reconfigurable optical add-drop multiplexers are also exploited. ROADMs allow individual or multiple wavelengths carrying data channels to be added or dropped from a fiber without the need to convert them to electronic signals and back again to optical. By combining these technologies, 5G PHOS proposes a converged fiber wireless cost-efficient solution. With massive-MIMO-enabled RRHs, several beams can be produced through a single fiber with wavelength division multiplexing. Furthermore, analog radio over fiber transmission enables the use of higher-order modulation schemes, resulting in low complexity and high spectral efficiency. Thereby, 5G PHOS can offer data rates up to 100 gigabits per second, decreased energy consumption by a factor of 10, while efficiently facing the CPRI inefficiency problem. 5G PHOS will provide solutions for dense networks directly applicable to fiber-to-the-home networks, ultra-dense, as well as for hotspots. 5G PHOS is a 3-year 5G PPP Phase 2 project on 5G integrated fiber wireless networks, launched in September 2017. 5G PHOS brings together 16 partners from 8 countries, being led by the Aristotle University of Thessaloniki. 5G PHOS solutions will be tested through lab and field trials at the Orange Labs in France, the deployed network of Telecom Italia in Cosmote, Greece, and at the stadium of PAOK FC in Greece.